Welcome back. In the last video, we finished off by finding exact values for sine and cosine for multiples of 30, 45, and 60. In this video, we're going to start off by looking at the other four trig functions and evaluating them. And it's not really much more involved, really just one extra step beyond what we've already done. So if you were looking for something like cosecant of pi over 3, the only thing extra that I would need to do would be to remind myself that cosecant is the reciprocal of sine. So I would need to first begin by finding what is sine of pi over 3 and then flipping it. So I start off by thinking about pi over 3, and I know for sine of pi over 3, sine would be opposite over hypotenuse, root 3 over 2. So that means for cosecant, it should be the reciprocal, 2 over root 3. And then, of course, the usual, making sure that our answer is in simplest terms, so rationalizing our denominator. And we found cosecant of pi over 3 is 2 root 3 over 3. If we've got an angle that's not just 30, 45, or 60, then we're also going to have to think about reference angles and quadrants. So first, before I get into that, I'm looking for secant of 330, and I know to find secant, I'm going to do that by thinking about cosine instead, because cosine is the reciprocal of secant. So first, I'm going to think about what is cosine of 330, and then once I find that, flip it, and that will give me secant of 330. And for 330 degrees, we know where that is. 330 degrees is over here in quadrant 4, and it should have a reference angle of 30 degrees. So let's do our work here. First, thinking about what is cosine of 30 degrees. And for 30 degrees, pi over 6, cosine is adjacent over hypotenuse, or root 3 over 2. The next thing is we have to think about our quadrant. Is cosine going to be positive or negative? And our quadrant that we're in happens to be quadrant 4, and in quadrant 4, cosine happens to be positive. So that means we now also know cosine of 330 degrees should be also positive, root 3 over 2. So that means if we were looking for secant of 330 degrees, now that we know what cosine of 330 degrees is, secant should just be the reciprocal. Cosine of 330 is root 3 over 2, positive. So secant of 330 should be the reciprocal, 2 over root 3. And of course, rationalize our denominator. So 2 root 3 over 3. Okay, cotangent of 4 pi over 3. So for this one, I'm going to, again, think about reciprocals, because if I want cotangent of 4 pi over 3, I'm going to use the fact that cotangent is the reciprocal of tangent. So first I'd be thinking about what is tangent of 4 pi over 3, and then once I know that, I can use that to find cotangent of 4 pi over 3. As far as the angle goes, we know that pi would be out here, which is the same thing as 3 pi over 3. So since it's 3 pi over 3 to get to the negative x-axis, then 4 pi over 3 should just be a little bit beyond that. And it should be beyond it by exactly pi over 3. So pi over 3, that's my reference angle. So let's start off with first finding what is tangent of pi over 3. Once I know what that is, then I can find tangent of 4 pi over 3, and then once I know what that is, then I can find cotangent of 4 pi over 3. Okay, so special triangles. Looking at pi over 3, tangent is opposite over adjacent, and for pi over 3, the opposite side is root 3, and the adjacent side is 1, so root 3 over 1. And the next part, of course, is our quadrants, and the angle that we're looking at happens to be in quadrant 3, and in quadrant 3, that's where tangent happens to be positive, so we actually also know that tangent of 4 pi over 3 should also be positive root 3 over 1. Okay, so we found most of what we need. We know what tangent of pi over 3 is. That led us to find what tangent of 4 pi over 3 is. And as our last move, we just have to say, well, cotangent is the reciprocal of tangent. And since tangent was equal to root 3 over 1, then cotangent should be the reciprocal of that. It should be 1 over root 3. And of course, rationalizing our denominators to give us tangent of 4 pi over 3 being equal to root 3 over 3. Okay, so here we're going to start talking about some other properties that the trig functions have and how that can help us with our evaluating. And so the first thing to talk about is that some of our trig functions turn out to be even functions and some of them turn out to be odd functions. And so I'm going to explain which ones are which and why. Here I've drawn an angle in standard position and I've drawn my angle positive theta. And if I thought about drawing negative theta, so instead of traveling theta degrees in the counterclockwise direction, if I traveled theta degrees in the counterclockwise direction, then the angle that I'm talking about is really just the mirror image of the one that I have on top. In fact, you could think about the angle on the top is just reflected in the x-axis to give me the angle that's on the bottom. That also means two things. If you're thinking about we have a point on our terminal side xy when the angle was positive theta, since the negative angle is just the mirror image flipped in the x-axis, then you'll have a point with the same x-coordinate, but you'll have the opposite sign for the y-coordinate. So instead of the y value being positive, the y value would be negative. And of course, since these are mirror images, the length r from 0 to the point for the positive angle would be the same as the length from 0 to the point for our negative angle. So that means that for negative angle theta, x is staying the same and r is staying the same. So that means the trig functions in terms of x's and r's, cosine and secant, those should both stay the same. If you're thinking about, for example, cosine of negative theta, that would be cosine of negative theta would be the x value over the value of r. And that's the same thing as cosine of positive theta would be the x value over r. Since the x values and the r's are the same, whether it's positive theta or negative theta, then cos of negative theta is equal to cos of theta. In other words, cosine happens to be even. And you could make a similar sort of argument that sine would have to be odd, because, for example, sine of negative theta should be the y value divided by r. And you know for sine of positive theta, it should also be the y value divided by r, except its y value is positive. You know that sine of positive theta is positive y over r, so sine of negative theta is the negative of sine of positive theta. In other words, sine of negative theta is the opposite sign of sine of theta. In other words, sine happens to be an odd function. So I'm not going to go and derive all of them for all 6 of the trig functions. One thing I can just sort of point out, and this is the easier way to remember it, is that there's only 2 trig functions that happen to be even, and the rest of them all happen to be odd. So for something like cosine, that happens to be an even function. Cosine of negative theta is cosine of theta. And same thing for secant. It's also an even function. Secant of negative theta is the same thing as secant of theta. But the rest of the other trig functions are all odd. Sine of negative theta is the opposite of sine of theta. Tangent of negative theta is the opposite of tangent of theta. And same thing for cosecant, and same thing for cotangent. So this is giving us a nice little way to deal with negative angles, because, for example, if somebody asks you to find cosine of negative 30 degrees, you don't have to draw negative 30 degrees. You can just say, oh, well, courtesy of the fact that cosine is even, cosine of negative 30 should be the same thing as cosine of positive 30. And then that simplified your life quite a bit. So that means that we'll never really have to deal with negative angles as long as we know which trig functions are even and which ones are odd. So let's do a couple of examples involving these symmetries. First one I want to find out is what is secant of negative 30 degrees. So first thing that I would do would be to say to myself, well, number one, I know that secant is the reciprocal of cosine. So secant of negative 30 is the same thing as 1 over cosine of negative 30. And the second thing that I know is that cosine is an even function, so cosine of negative 30 and cosine of positive 30 are the same. So in other words, I really just need to find the reciprocal of cosine of positive 30 degrees. And for that, I just need to use my special triangle. For 30 degrees, cosine is adjacent over hypotenuse, root 3 over 2. And so secant is the reciprocal, 2 over root 3. Which, of course, rationalize your denominator, and there you go. Now, you could always do this the other way being drawing your angle and dealing with quadrants and all the rest. So you could, if you felt like it, draw an angle of negative 30 degrees, at which point you'd realize that the reference angle should be 30. You'd have to find cosine of 30. You'd have to think of quadrants. Eventually you'll get there, but I think one of the nicer things is if you can use symmetry, just like if you can use identities, it will save you time and save you effort. So here I use the fact that secant was an even function as is cosine, so that took care of the negative angle. So all I had to deal with was the angle in a positive version. All right, so same sort of a thing here. I'm looking for tangent of a negative angle, tangent of negative 4 pi over 3, and I'm going to use what I know, which is that tangent is an odd function. So instead of tangent absorbing that negative, the negative will come on outside. I'll have tangent of negative 4 pi over 3 is negative tangent of 4 pi over 3. So now my plan is I'm going to find tangent of 4 pi over 3, and then once I find that, I just need to change its sign, and that'll be tangent of negative 4 pi over 3. And of course, to find tangent of 4 pi over 3, first thing I would have to do would be to draw my angle. So there's pi, there's 3 pi over 3, so 4 pi over 3 is just a little bit past it, and it's past it by pi over 3. So pi over 3, there's my reference angle. So I'm going to do my work on the side here and say to myself, number one, I can first figure out what is tangent of pi over 3. Tangent of pi over 3, tangent is opposite over adjacent, or root 3 divided by 1, or just root 3. I know, courtesy of the quadrant that we're in, we are in quadrant 3, and in quadrant 3, tangent happens to be positive. So tangent of 4 pi over 3 should also be positive root 3. And so now I can finish things off. I can say to myself, well, I know tangent of negative 4 pi over 3 is the negative of tangent of 4 pi over 3, and I know tangent of 4 pi over 3 is root 3, so my answer is negative of root 3, or negative root 3. Now, one other little property that we can sometimes use to make our life a little bit easier is the fact that our trig functions are periodic. In other words, they repeat their values over and over again. And that's probably not a big surprise if we're going back and thinking about our unit circle definition. If we're thinking back to when we first talked about the domain and range of sine and cosine, one of the things that I pointed out was The values for sine are going to alternate, going from 0 to 1 to 0 to -1 to back to 0. And as our angle increases, we're just going to go through those same values over and over and over again. That once we've done a full circle, once we've done a full 360 degrees, we're just going to repeat our same values for sine over and over again. The same thing is also true for cosine and all the other trig functions. One of the nice things is most of our trig functions have a period of 360 degrees, or 2 pi. So sine, for cosine, for secant and cosecant, they all repeat themselves every every 360 degrees, or every 2 pi radians. But for tangent and for cotangent, they have a shorter period. They repeat themselves every 180 degrees, or every pi radians. So, for example, if we're looking to find the exact value of a trig function, like tangent of 225 degrees, I could always draw the 225 degrees, but I could remind myself that since tangent repeats itself every 180 degrees, and I know that 225 degrees is the same thing as 180 degrees plus 45, then I know that whatever value tangent has for 45 degrees, it's going to repeat that value at 225. And it will repeat it another 180 degrees after that, and it will repeat it another 180 degrees after that, and so on. So actually, I could use what I know about the periodicity of tangent to say tangent of 225 should be the same thing as tangent of 45, and that's because these two angles are differing from each other by 180 degrees, and tangent repeats itself every 180 degrees. So I can then say, based on my special triangle, tangent should be opposite over adjacent, or tangent should be 1 divided by 1, or just 1. If you didn't think to use periodicity here to help simplify your work, that's fine. You could always just draw your angle of 225 degrees, find your reference angle, and do the usual. But as always, the more that you know, the easier things will be. So if you know about the periodicity of our functions, and you know how often tangent repeats itself, and you think to use that, then actually that makes your work a lot shorter and a lot easier. All right, so there's one last one that I want to work through, and this one, secant of -7 pi over 3. I just sort of want to talk out loud about what if you didn't notice any of the identities that you can use to help make your life easy. So if I wasn't thinking about symmetry, if I wasn't thinking about periodicity, then I would first have to start by drawing -7 pi over 3. I'd have to say, well, you're going 7 pi over 3 radians in a clockwise direction. I'd have to think about the fact that 2 pi, or 6 pi over 3, is a full circle. So -6 pi over 3 is traveling a full circle clockwise. So -7 pi over 3 is traveling more than a full circle clockwise. I'd have to think about reference angles. I'd have to think about the fact that secant and cosine are reciprocals. I'd have to think about quadrants. There would be really a lot for me to think about with this one problem. But I'm going to show you how, with a little bit of extra work, just thinking about periodicity and symmetry, I've got way less effort to think about, or way less effort to put in. The first I'm going to think about is the fact that secant and cosine are both even functions. So I know that secant of 7 pi over 3 is the same thing as secant of +7 pi over 3. So already I've made my life a little bit easier by saying that I can just ignore the negative because secant happens to be an even function. The second thing that I'm going to note, and I kind of already said this when I pointed out that 7 pi over 3 is more than a full circle, that 7 pi over 3 is the same thing as pi over 3 plus a full circle being 2 pi, or 6 pi over 3. So in other words, if I'm thinking about my value for what is secant of 7 pi over 3, since 7 pi over 3 and pi over 3 are one full circle apart from each other, secant of 7 pi over 3 and secant of pi over 3 should both be equal. And then finally, I'm going to think about the fact that I know that secant and cosine are reciprocals of each other, so secant of pi over 3 should just be the reciprocal of cosine of pi over 3. So all I really need to do here now is just use my special triangles, find cosine of pi over 3, cosine of pi over 3 being adjacent over hypotenuse, 1 over 2. So secant should be the reciprocal, 2 over 1, or just 2. So you'll notice I didn't have to draw an angle, I didn't have to think about reference angles, because I thought about using symmetry, the fact that secant is even, using periodicity, using the fact that the 7 pi over 3 and pi over 3 are one full circle apart, using my reciprocal property, secant and cosine are reciprocals, I was able to jump directly to finding the exact value of secant negative 7 pi over 3 being equal to 2.